Hola, Team Bio. Okay, so today's screencast is going to be on evidence of evolution. So we have this theory, this idea of evolution and how it works. But I want to talk to you about some of the pieces of evidence that support this theory. So the first piece of evidence is actually buried within the fossil record. So if we look at, okay, I guess that's fine. If we look at the Earth, and imagine we take a cross-section of the Earth. Each of these lines represents layers of rock, and the rock at the bottom is going to be the oldest, and the rock at the top is the youngest. And so the rock that was laid down in the most ancient times is down here, and fossils that we find down in this oldest section, we can actually track their development or their changes over time. So let's say we started with an organism that looks like this in the oldest rock, and then we see in the next oldest rock that it looks something like this, and then in the next one it looks like this, and then it looks like that, and so on and so forth, up until the newest generation, where it looks something like this. This would be pretty good evidence that this organism is changing over time. And so I'm just going to flash up a picture here on the screen for you. Okay, so here are scallops found in the Chesapeake Bay, and as you can see, these are most ancient scallops found in the bay, and they have changed over time. So if you look at the space between the ridges, it's gotten and fewer ridges over time. The space has decreased between them, or increased, and they've gotten fewer ridges over time. But you can see the resemblance of this primordial scallop to this more recent scallop, and how they progressively change throughout the ages. So the fossil record is just the first piece of evidence for evolution. Okay, the next piece of evidence for evolution is called homologous structures. Okay, so this is an example of homologous structures. So here are diagrams, not to scale, of bones found in the limbs of humans, horses, cats, bats, birds, and whales. And you'll notice here that we all have, although the bones are different sizes and different shapes, we all share the same basic body plan. We all have some kind of large top bone that has a ball and socket joint at the top, and then some sort of radius and ulna bone, although you can see that in some of these organisms the radial bone is no longer there, and then we all have some type of phalanges, some type of fingers. And this is true across all these organisms. Like birds aren't even mammals, and yet they have the same basic body plan. And you can see that it's been changed over time. So, for example, whales have much longer phalanges than we do, or horses do, and this is because those have expanded obviously into their flippers, but they still carry the same. It looks like a whale. Basically, you squished the radius and ulna and the humerus, but you can still see we share the same basic bone structure as a whale. So the most obvious explanation, or the most likely explanation you have for the fact that we all share these homologous structures, is that we all evolved from some common ancestor that also had this basic body plan, different types of bones. Okay, so that's the next piece. The next piece is pretty cool. Okay, so the next piece is called ontogeny. And ontogeny is basically the way that an embryo develops. So I'm going to flash up a brief picture here. Okay, so here's the picture, and this is really quite striking. So these are fish, salamander, turtle, chicken, rabbit, and human embryos. Just a few, well, it depends on the organism, but they're early in embryonic development. And you can see that they all look remarkably similar. And this is because the genes that are responsible for early patterning, basically what's going to become your head and your butt. So the Frank Lynch. Hi Sam, how's it going? Good. I'm recording a screencast for Bio 400, so you can say hi to them.
Who's in Bio 400?
Lots of people.
Hi. Is that it?
That's all you're going to say?
That's all I'm going to say.
Okay. So, before Sam so rudely interrupted, you don't have to leave. If you want to listen, that's fine, but it's pretty boring, so. I mean, it's fascinating. No, it's pretty interesting stuff, actually. Okay. So, dorsal ventral, and so the patterning that decides, okay, where's your butt going to go, where's your head going to go, where's your back going to go, where is your tummy going to go, that all happens really early on in development. And you can see that we share the same basic body plan as a fish and a salamander. So this is another piece of evidence that supports the theory of evolution. Okay. And our last piece of evidence to support the theory of evolution is, okay, here's a screenshot of a picture that I took of a New York Times article that I actually sent you early on in the term. But you might not believe this, but this is a tree. And it's a tree that shows genetic relatedness. So if you look way down into the tree right here, the way you read this is that this node that all the branches come off represents the origin of life. Or actually, I guess the origin of life would be somewhere right around here. Why is this? Why won't you let me move that? Okay, well. This is strange. Okay, so origin of life happened somewhere right back in here. And then all the diversity that we see currently in the world is at the tips of every point. And so here are bacteria, and archaea are over here. And, oh, no, sorry. These are all bacteria. Woo, bacteria is very diverse. Archaea are over here. And then all of eukaryotes, so probably what you think of as life, plants, animals, fungi, protists, we are all just this little section of the tree, which is pretty amazing. So yeah, this is the diversity of life, or this is showing a tree of life. And the reason why this is evidence for evolution, the way this tree is formulated is that you take genetic sequences of a bunch of different organisms, and then you see how closely related they are to one another. The more similar they are, so like for example, we share 98% of the same DNA as chimps, so that means that we diverged from chimps relatively recently in evolutionary history. Now, you might not think you have a lot in common with the bacteria, but you actually do share some similar genes. I mean, the genetic code is universal, so even that itself is evidence for evolution. Okay, but back to the point. All the genomes of all these organisms are sequenced, and then they're put into clumps based on how closely those genomes resemble one another, and that is the way the tree is formed. Hi guys. Okay, so I think that this is the end of the screencast because I'm done and everyone is here for class.
Screencast, it's me, Truant.
Can we be part of this?
Do you guys want to say something?
Yeah.
Hi,
Bio
Team Bio.
400?
What is this?
400. Ooh.
Bio
400?
Wait, isn't that normal bio?
Yeah.
Stay in school and don't do drugs.
Yeah, what we learned from econ, don't smoke.
Okay, perfect. That's a great way to sign off. Okay, done.